Given parallelogram ABCD, I need to prove that AB, that one, is congruent to DC, that one, and AD is congruent to BC. This is one of those types of proofs where you want to look at this and say, well, isn't that the definition of parallelogram? So it's like a two-stepper? No, this is one of those things where we are trying to prove a theorem, and the theorem is parallelograms have opposite sides that are congruent. So we already know this. We just need to prove it. So what do we know? Well, it gives us these little markings here that tell us that they're parallel. So it says parallelogram, so we know that they're parallel. We know that they're parallel. And usually when they give you parallel information, you're thinking alternate interior angle thoughts. So I'm going to do this. I'm going to focus on AB and DC, and I'm going to say that these two guys are congruent because they're alternate interior angles. And I'm also going to say that these two guys are congruent for the same exact reason, alternate interior angles. Now, if I say that, and if I also say that AC is congruent to AC, then I have these two triangles are congruent to each other using ASA. And since ASA tells me that these guys are congruent triangles, that means these sides are congruent and these guys are congruent by CPCTC. Congruent parts of congruent triangles are congruent. No, corresponding parts of congruent triangles are congruent. Tough one. So that's what we're going to do. We're going to say, you guys are congruent, you guys are congruent, you guys are congruent, reflexive. Then we're going to say that the triangles are congruent. And then from there, we can do the proof by using CPCTC, and that should do it. So first things first, always the given. Okay, we are given a parallelogram ABCD, and that's our given. Now, this might be an unnecessary step, but there's no harm in doing it. Since it is a parallelogram, we will say that AB is parallel to DC. AB is parallel to DC. And I'll just say also that AD is parallel to BC. Okay, no harm in saying that. Didn't kill us. I'm still alive. That's the definition of parallelogram. Can I fit it in? I did. Barely. Looks sloppy, but I did. All right, now let's do our angles. Angle BAC. Let's do it in the colors that I gave them to you. Angle BAC. Let's do the measure of angle BAC is equal to the measure of angle BAC DCA. And for the red ones, we'll put it in red. The measure of angle DAC is equal to the measure of angle BCA. Forgot to say the measure of angle. Don't want to be wrong. The measure of angle, what did I say, BCA? And that's the definition of alternate interior angles. All right. So I have two angles and I need the included side. So the included side is literally a side that's being shared. We could say that AC is equal to AC, and that's the reflexive property. Whenever you say something is equal to itself, it's always the reflexive property. Now that I used angle, side, angle, I can say that those triangles, and let's make sure we have it in order. Let's do ACD. Triangle ACD is congruent to red, purple, so CAB. And that is ASA. And since these guys are completely congruent, now we could say AD is congruent to BC, boop, and AD is congruent to BC, so that'll be our last step. Let's see if I can fit that in. AB is congruent to DC, comma, AD is congruent to BC, and that is corresponding parts of congruent triangles are congruent. All right? So again, this is one of those proofs where you're proving an actual theorem. Okay, it's not as simple as you saying, well, my book says theorem 6.12b says that parallelograms have opposite sides that are congruent. So can I just do a two-stepper? Technically, yes, but we wanted to show the actual proof of that, and that's what we did. Dunzo.